So we've just considered polynomials that are identical, and we've reasoned that if we know the degree of the two polynomials that may or may not be the same polynomial, and we find a certain number of intersections that is more than that degree, then they are in fact the same polynomial. That makes heaps of sense if you consider that two straight lines might cross in one place, assuming they're not parallel. But if they cross in two places, they are in fact the same straight line. We know that for two parabolas to be the same parabola, they must share not just 2, but 3 points, okay? Because the degree of a parabola is 2. So if they're sharing 3 points, they are in fact the same parabola. But the reverse is also true. So this lets us find some information about the number of intersections we're expecting between two polynomials that are not identical. So if we say that P and X and Q of X are not identical, and the highest degree of either one of them is n, then we can reason that they mustn't be intersecting any more than n times. So in this question, we need to think about how many intersections could possibly exist between two polynomials. Now we know that a and b are not equal to 0, so we're assuming here that they are some other constants. And what we can see straight away is that we've got a quartic curve because the highest power of x is 4, and we've got a parabola or a quadratic function, and I can tell that because the highest power of x is 2. So the higher one of either one of them is 4. And that tells me it's probably got that sort of W shape, or it could be upside down like a sort of M shape. It could even be a sort of fat-bottomed parabola either way up, because I don't know the values of A here. But what I do know is that it can't intersect with this other one any more than 4 times. If it did, they'd be the same polynomial, and I can tell they're not the same polynomial because they've got a different power of x. And that's assuming that A isn't 0, of course. In this next one, I've got a straight line and I've got a cubic curve. So assuming that, again, A, B and C are not equal to 0, they've got a different highest power of x. And so the higher one is the 3, and I can tell that this cubic curve can't intersect a line any more than 3 times. And that makes complete sense if we think of the shape of a complicated cubic curve. The most sort of complicated it can get is to have a wobble in it. And if we've got a straight line crossing it, there's a chance that it only crosses it once. There's a chance that it doesn't cross it at all. There's a chance it might cross it twice, perhaps it crosses here and then just touches here, or perhaps it crosses it 3 times. So we can't tell how many intersections there are, but we can tell what the maximum might be. And in this case, it'll be anything up to 3 intersections, and in this case, it'll be anything up to 4. Now we've looked for intersections of polynomials before, especially where 2 straight lines cross each other, or where a straight line crosses a parabola. And the method that we've always used is to just solve the 2 equations simultaneously. So if we have y equals something and y equals something else, we're quite used to writing those above each other, calling them equation 1 and equation 2. And then we can say, well, if y equals this and y equals that, by substitution, all of this would equal all of that. And we can write a line like this. Now, when we're working with polynomials and we've got higher powers of x than just x squared, obviously we can create an equation that might be quite hard to solve. But our usual method of solving simultaneously is actually really important in understanding how we can use the same method when the equations are a little bit more complicated. Now, what's the first thing that you might do to tidy this up? Well, we know that when we're solving equations, a really good strategy is getting everything on one side and letting the other side equal 0, so that then hopefully you can factorise it, and then you can reason that something times something equals 0, so one of those parts must be 0. So the first thing I'm inclined to do here is actually consider taking this whole left-hand side of the equation and subtracting the whole right-hand side of the equation, or vice versa, of course. Now, perhaps we can do this in our head. I'm just making it really clear what I'm actually doing here. Obviously, I'm going to need to be careful to avoid a sign error here, and that set of brackets is going to change the sign of everything, minus 3x cubed minus 3x. And then I can tidy up and see that my x to the power of 4 is gone now. I've got 4x cubed minus 3x cubed, so that's just giving me x cubed. And I've got negative 3 x's, and I've got plus 2, and all of that equals 0. So straight away I'm in a better place and I've sort of tidied up. But let's just pause for a moment and consider what we did. We basically took all of p of x, what it was equal to, and we subtracted q of x. Now if we consider that what we've created is a polynomial in its own right, we could call it, well, we've got P of x and Q of x, let's call it R of x, say. Then if we use our factor theorem and investigate some possible values here, like for example, we could try R of 1, -1, I think 2 and -2, they all make sense because it's a monic one and my constant here is 2, so I'm thinking most of my factors are going to be things like x plus 1, x minus 1, x plus 2, x minus 2. I can try these, and it's quite a simple one to do by hand. Trying 1 in here for x, I've got 1 minus 3, that's -2, plus 2, that does equal 0. Therefore, I can see that x minus 1 is a factor of this new polynomial, which we're calling R of x. Testing -1, I'd have -1 plus 3 plus 2, that's not going to equal 0. Trying 2, I'm going to get 8, minus 6, that's 2 plus 2, that doesn't work. R of -2, we'll have -8, plus 6, plus 2, that will work. So I can see here that x plus 2 is also a factor. Now I'm narrowing things down here. If I'm trying to factorize this, what I've already discovered is that I've got x minus 2 and, x minus 1 and x plus 2 as factors. All right, now multiplying them together, the lasts, I get -2, and I need +2. So it's a fairly good guess that my other factor is in fact another one of these. How can I tell? Well, I've got x cubed here, so I know that the third factor, if I was to find another little set of brackets to put in here, and I know I need another one to get my x cubed, so my firsts are right. It makes sense to say, well, I know these two, and they need to multiply together to make 2. So it sort of has to be -1. And then instead of writing it like this, I can write it like that. Now at that point, I can say all of that is equal to 0. So that means that this part was 0, which would mean that x was 1. Or this part was 0, which would mean that x is -2. Now, what are we trying to do here? We're trying to find the intersections of these two polynomials. So we've just found the x values of 2 of the intersections. So we've got 1 something, and we've got -2 something. How do I find the other one? Well, I can plug either of those x values back into either of these original polynomials to find the y value. Now that whole method should have made sense to you just as a concept, to be able to solve 2 equations simultaneously, to solve for x and then sub back in and solve for y. But in this topic, what we've frequently done is we've learned how to do something algebraically, and we've also learned how to do it graphically. So that when we see a graph and we don't know the equation of it, we can actually make some sensible inferences about those intersections. Now the same concept, if I show it graphically in a situation where I don't actually know the equations of y equals p of x or y equals q of x, will help us understand how this polynomial that we make when we subtract one polynomial from the other can help us find information, if we didn't know how to graph our polynomials, about where one of our curves is going to lie above or below the other one. Now, just looking at this red polynomial and the black one, and let's use our graphical skills to subtract the black one from the red one. So what we're actually finding here is p of x minus q of x. Now, if we did that, we've learnt some little hacks to spot key points, and we did this in chapter 5, further graphs. So what we said was, well, where the two are intersecting, so I can see that they meet here and here and here. If I take one number away from the other and those numbers are the same, I'm going to get 0. So whatever y value that equates to there, if they both have the same y value there and I take one away from the other, my new graph, this new polynomial that I get when I do this, is going to have a 0 right there at that value of x, if I just drop a line down. And similarly, whatever the height that is, the red height minus the height of the black one, it's going to have a 0 there. And similarly here, it's going to have a 0 here. So I can reason that my new polynomial, I don't know a lot about it at this point, but I do know that it's got zeros here, here, and here. Then I can say, all right, well, if I've got both of them being positive, in other words, between these two zeros, if I want to work out the sign of it, then if I'm doing the red one minus the black one and the black one is sitting above, then I've got a number take away a bigger number. It's going to be negative, isn't it? So between here and here, my new curve is definitely going to be negative. And in fact, even along here, if I've got my red one and it's a negative number and then I'm subtracting a positive number, it's still going to be negative. So I can see that my new curve is going to be negative all the way through from here to here. So I'll just sort of put in something to show that it's definitely sitting down here on the graph. On this side of the 0 of my new polynomial, I can see that at first I've got red being not quite such a small number as black. So let's think what it could be if it was like -1 minus 8. That'd be -1 plus 8. That would be a positive number, wouldn't it? And this is going to keep on happening. As I have a positive number minus a negative number, I'm going to get a positive number. So my new curve, which I'm doing in blue, is going to go shooting up somehow. It's definitely going to sit above the curve, isn't it? And between these two zeros, the red is a bigger height, if you like. My y values are bigger than my black ones, so it's going to be positive there too. So between here and here, I've definitely got a positive. And then what's going to happen over here? Well, I've got the red one, which is a negative number. Take away a positive number, and that's going to give me a negative number. So my good old strategy that I learned in chapter 5 of looking at the sign that I'm going to get when I take one polynomial away from the other is quite informative here. I can see that my new polynomial is going to have zeros where the intersections were, but I can also reason what the sign of my new polynomial will be in between. Now, how's this going to help us? Well, a moment ago we looked at finding the intersections between two curves. Remember, we had P of x and Q of x. You've already written this down in your notes. And in that first example, we just had to find the intersections. And so we took one curve away from the other. And the reason that we did that is we started to solve them simultaneously, and that just seemed to be a sensible first step. And we got a new polynomial. We called it R of x. We could have called it anything we like. And then we used our factor theorem and our understanding of the factors of a polynomial to factorise it. Okay, now after we've done that, we've reasoned that it's got zeros at 1 and -2. Now this question is marginally different, similar but slightly different. We want to now find where this polynomial lies above that one. So we've used this process to find the intersections. And what we've found is that if we take one polynomial away from the other, you've seen graphically how I just did that. We've generated a new polynomial. And that polynomial is going to have zeros here in this case. Now, we've also seen that if we know the new polynomial, we can graph that in its own right. And in the last example, I just did that, even not knowing the formulas for those polynomials. But this one I do have the formula for. And I can see that it's a cubic curve, so I know its basic shape. It's a positive one, so it goes from low to high. And it's got a double root at 1, and it's got a single root at -2. So it must go up through this one, and then just touch this one before going up again. I can also work out this if I like, which is going to be 2. Now, how am I going to use this to answer my question? Well, this curve represents what happens when you take one of these away from the other. If this curve was taller or higher up at certain points, in other words, it lay above this other one, then we'd expect that when we did the subtraction, we'd have something that's positive. Does that make sense? Now, where is this thing positive? I can easily see it's positive here and here. At this point here, it equals 0. Over there, it's less than 0. So I can see that this curve here must lie above that one any time that this polynomial is greater than 0. And so I can answer my question here by saying, well, that happens between x values of -2, but not equal to -2. It would be 0 then, so it wouldn't be above it, it would be right on it. Between 0 and 1, and then again when x is greater than 1. Now, this curve is not lying above that one when x is 1 or -2. It's sitting right on top of it. It's an intersection. So technically, I need these two parts to my answer. And if the question said, where does this polynomial lie below this one, then I'd have to reason that, well, if it's lying below, it must be that when we did the tall one, or the first one, minus the other one, we got a negative answer. So it must be lying below wherever our answer is negative. And that would happen when x is less than -2. Another quick example now. I want to see where this polynomial lies above this one. So I want to do this one minus this one and reason that anywhere my answer is positive, this one must have been the taller one, or the bigger number if you like. So I've written out what I'm going to subtract from what, and then I've got my first polynomial minus my second one, and now I need to just expand that. X cubed minus x cubed is going to disappear. I'm going to have negative x squared plus 2x, and I have minus 1 minus minus 4, that's plus 4, so that's going to give me plus 3. Now I find it easier to factorise this if I actually just bring the negative up front here, so that I'm dealing with positive x squareds. So that gives me this. And now I'm looking for factors of negative 3 that add to negative 2. So I want plus 1 and minus 3. So I can see that my new polynomial has got intersections at negative 1 and 3. They're my zeros, or my roots if you like. So now if I went to graph this thing, what sort of graph is it? My new polynomial r of x, which I could label all the way down here, of course. Well, it's a parabola. I can see that it's a quadratic function because it's got to the power of 2, but it's an upside down one. And so if I can reason that it's got zeros at negative 1 and at 3, and it goes upside down, then I can see that this curve is going to lie above this one. Remember I said that will happen anywhere that my subtraction is positive. And this is my subtraction, and it's positive from here to here. So I can reason that it happens in between the x values of negative 1 and 3.